In this segment, we're going to talk about temperature, thermal energy, and temperature conversion. Temperature is a measure of the velocity of random motions among the atoms or molecules in a material. Let's focus on this word material. What we mean by material is a gas, a liquid, a solid, or a plasma. A plasma is an ionized gas. It consists of positive ions and free electrons, and typically has no electric charge. And we usually find plasmas at very high temperatures, such as in stars or in nuclear fusion reactions. Here is an image from Hubble, and it's a picture of the Boomerang Nebula. It was taken with the advanced camera for surveys. It is a reflecting cloud of gas and dust. So we're looking at these two lobes above the star that has gas and dust in it. And we mainly want to focus on the gas part. So the material we'll be looking at in this case is the gas part of this nebula. So if we zoom in on this gas, and let's say we could actually look at the gas atoms and molecules, we might see something like this. So this is our gas, and the big particles are going to be our molecules. And the smaller particles are going to be our atoms. Now notice that these molecules are all moving in a particular direction, and so are the atoms. And I'm going to put the atoms in the green color, and the molecules in the red color. Now notice they are all moving in these random motions, these random directions. And they're all moving at different speeds. The bigger the line, the faster the speed, the smaller the line, the slower the speed. Say. Now speed is a number in a unit, such as 5 meters per second or 10 feet per minute or 45 miles per hour. Velocity, on the other hand, is the number plus a unit and a direction. So the difference is with velocity, you have to include the direction. And examples would include 5 meters per second and the direction might be north, or 10 feet per minute and the direction would be southeast, and 45 miles per hour in the forward direction. So if we had a scale that I have drawn up here where up is in the northerly direction, down is in the southerly direction, to the right is east, and to the left is west, then we can look at this molecule and see that it is moving pretty fast in the southerly direction. And this atom is moving equally as fast in the northwest direction. So if we could take all the particles that we see here and add up all of their velocities, all of their directions, plus all of their speeds, and add them all up and find an average, then that average value would equal or be equivalent to the temperature of the gas. So I'm going to add this word average to this definition. Temperature is an average measure of the velocity of random motions among the particles in the material, in this case, the gas in the nebula. Now let's look at thermal energy. Thermal energy is the energy stored in an object as agitation among its atoms and molecules. So let's bring in this cartoon again of the gas, and we see the molecules in red, the big particles, and they're all moving in their random directions. And we see the atoms in green, and they too are moving in their random directions. Now each particle has an energy E, and that energy is equal to the mass of the particle times the velocity of the particle squared divided by 2. So if we could add up all of the energies of the individual molecules and particles, then we would get what is known as the thermal energy. So I'm going to add a word to this definition. It is the total energy stored in an object as agitation among its particles and molecules. And of course we must include any particles that are not moving, so any stored energy. So whereas temperature is the average, thermal energy is the total. For temperature, we take the average motions of the particles, and for thermal energy, we add up all the motions of the particles. So the hotter an object is, the more thermal energy it will have, as well as it will have a higher temperature. The colder an object is, the lower thermal energy it has, and the cooler temperature will have less of a temperature, less temperature, or a cooler temperature. The hotter the object, the faster the particles are moving in the material. The colder the object, the slower the atoms and molecules are moving in the material. So keep in mind that temperature refers to the average speed of the particles in the material, whereas thermal energy refers to the total speed of the particle, or the total energy stored in the gas. It is the sum of the particles' speeds. So for example, you could have hot cheese and you could have hot green beans, and both the cheese and the green beans are at the same temperature. But you could burn yourself on the cheese and not on the green beans, even though they're at the same temperature, because the cheese has a higher thermal energy. So not only do you have to take into account the speeds or the velocities of the particles, but you also have to also take into account the mass of each individual particles. The more particles you have, the higher the thermal energy. The cheese may have more particles than the green beans. Let's look at temperature conversion. Let's look at temperature conversions among the 3 temperature scales. We have the Kelvin temperature scale, we have the degree Celsius temperature scale, and we have the degree Fahrenheit temperature scale. So depending on which part of the world you are from, you may be more familiar with Celsius compared to Fahrenheit. In science, we use Kelvin. So we're going to do the conversions among the 3 temperature scales. In the Fahrenheit scale, water boils at a temperature of 212 degrees Fahrenheit. In the Celsius scale, it's 100 degrees Celsius. In the Kelvin scale, it is 373 Kelvin. Now notice I said degree Fahrenheit, degree Celsius, but not degree Kelvin. There is no degrees with Kelvin. You just say Kelvin. Now let's look at when water freezes. Water freezes in the Fahrenheit scale at 32 degrees Fahrenheit. In the Celsius scale, it is 0 degrees Celsius. In the Kelvin scale, it is 273 Kelvin. Now let's look at absolute zero. Absolute zero is the lowest possible temperature in a material. It is the temperature at which the particles in a material, such as the atoms or molecules, contain no energy of motion that can be extracted from the body. Absolute zero is when the particles don't move. So remember, temperature is the average motion of the particles, whereas thermal energy is the total motion of the particles. In absolute zero, the particles aren't moving at all. So on the Kelvin scale, absolute zero is 0. Now on the Celsius scale, to make the equivalent, we would have to set it at minus 273 degrees Celsius. And on the Fahrenheit scale, we would have to set it at minus 460 degrees Fahrenheit. So in science, we have the scale correct where 0 is at the bottom, indicating no motions of the particles, and where water boils, you have the highest number, indicating the highest average temperature of the average motions of the particles in that substance. Now let's look at temperature conversions. We want to convert from one temperature scale to another temperature scale. Let's say you want to convert from Fahrenheit to Celsius. We have this equation that says the degrees in Celsius is equal to 5/9 times the parentheses of the degrees in Fahrenheit minus 32. Let's do an example. Let's say you're given Pluto. Well, the temperature of Pluto at its surface is around minus 388 degrees Fahrenheit, say. And let's say you wanted to find the degrees Celsius. You would use the equation degrees Celsius is equal to 5/9 times the parentheses of degrees Fahrenheit minus 32. So we plug in minus 388 degrees Fahrenheit where we see the degree Fahrenheit symbol. So we have minus 388 degrees Fahrenheit minus 32 degrees Fahrenheit, and we solve. First thing is we take minus 388 and we subtract minus 32 and we get minus 420. Then we multiply by 5 and divide by 9. And you should get a value of minus 233, and the unit would be degrees Celsius. Now what is this value on the Kelvin scale? To convert from Celsius to Kelvin, you take 273 and you add on that degree Celsius value. So let's say you have Pluto, and you know that its surface temperature is minus 233 degrees Celsius. We want to find out what it is in Kelvin, so let's solve. The Kelvin is equal to 273, and then we're going to add on minus 233, so we minus 233 degrees Celsius, and we get 40 degrees Celsius. Now, Pluto's surface temperature in the wintertime is 33 Kelvin in its wintertime, and Pluto's average surface temperature in its summertime is 55 Kelvin, so the average would be around 40 Kelvin. So even though we subtracted 273 minus 233 and we have units of Celsius, we don't put the units of Celsius down from the subtraction. We're doing a conversion, so we put Kelvin down. So the answer would be 40 Kelvin. So here we have our conversion from Celsius to Fahrenheit, and here we have our conversion from Kelvin to Celsius. What about the conversion from Celsius to Fahrenheit? The equation is for degrees Fahrenheit, that's equal to 9/5 times the degrees Celsius plus 32 degrees Celsius. Let's say you're given the degrees Celsius is 0, or you're looking at the temperature at which water freezes. Find the equivalent degrees Fahrenheit. Well, the solution, we're going to use that equation that we have up there, is that the degrees Fahrenheit is equal to 9/5, and we substitute in 0 for degrees Celsius, and we add on 32. So we get a value, this goes out, and we're left with 32. So our degrees Fahrenheit is 32 degrees Fahrenheit. And that makes sense because the temperature at which water freezes, the relationship between Fahrenheit and Celsius is 0 to 32. So this degree Fahrenheit is equal to 9/5 degrees Celsius plus 32 is actually our third equation, converting the temperature scale units. Let's do another example. Let's say you're looking at the temperature of 540 degrees Celsius. What is the equivalent temperature in Kelvin? Let's use that equation. Kelvin is equal to 273 plus 540. And we add them together, and we get 813 Kelvin, which might seem like a hot temperature to you. But let's look at some typical pictures of hot and cold objects. In this diagram, we're looking at the typical solar system, planets, and other objects in our solar system, and their average surface temperatures. And we're looking at the comparison between the Fahrenheit, Celsius, and Kelvin scales. Of these objects in our solar system, Pluto is the coldest surface, and Venus has the hottest surface. Even though Mercury is closer to the Sun, it is actually second hottest of the planets in our solar system. Venus is actually hotter. And then the rest of the planets go in the order that you would expect: Earth, Mars, Jupiter, Saturn, Uranus, Neptune, which increase with distance from the Sun. Now, what about the gases in this Boomerang Nebula? So we're looking at these gases that are just above the star, and the star is located in the center. So we're looking at the gases, and we want to know what is the temperature of these gases. And look at notice we have space out here as well, the black space that are surrounding it. If I asked you the question of which is the colder object on average, is the black space the average temperature colder, or is the gas in the Boomerang Nebula colder? And the answer is actually that the Boomerang temperature is actually colder than the space temperature. The Boomerang Nebula has an average temperature of 1 Kelvin in that gas, and that is much less than the space temperature, the black space that you see, that has an average temperature of around 3 Kelvin. So where would this Boomerang Nebula fit in this chart that we have of the Celsius and Fahrenheit scale? The Boomerang Nebula would be off the chart. It is all the way down at the bottom of the scale. If this is where 33 Kelvin is, then very near 1 Kelvin has got to be close to right about there, or minus 460 degrees Fahrenheit. It is 1 degree above absolute zero. And so this is where the Boomerang Nebula would fit. Now let's enlarge this scale to not just go to 813 Kelvin and down to about 33 Kelvin. Let's extend it from 0 up into the millions of Kelvin. When we're looking at this temperature range from 0 Kelvin up to 273 Kelvin, we are looking at very, very cold objects. Remember, 273 Kelvin is at the temperature at which water freezes. So let's draw a block of water ice to represent 273 and water freezing. Ice is a solid, so what we have here for water is we have a solid ice at 273 Kelvin. Now in between 273 Kelvin and 373 Kelvin, we have water in the liquid state. Remember, 373 Kelvin is when water boils. So let's look at water in the liquid state. So here I drew a water wave, and so we're looking at somewhere between 273 and 373, and it is water in the liquid state. Now at 373, this is where water boils. And so I have drawn here a pot of boiling water, and steam is coming off this boiling pot of water, and so the water is now in this gas phase. So as we increase the temperature of this steam into the thousands of Kelvin, what happens to the gas? So I'm going to put a little jog in our temperature scale here, showing that it's not to scale. And what we have is we're increasing the temperature into the thousands and increasing it even more into the millions of Kelvin. And we want to know what's going to happen to this steam. Well, the steam is actually going to turn into a plasma state. And remember, the plasma phase is where the free electrons are moving among the positively charged ions. So what's going on between the solid, liquid, gas, and plasma state, between the molecules and the atoms? In the solid state, I have all these molecules or atoms drawn as dots, and they're all connected together. So what happens when we increase the temperature and we go to a liquid state? In a liquid state, only some of the atoms and molecules are connected together, and the other ones are free to roam about. When we get to a gas phase, we increase the temperature some more. They're all free particles running around. The atoms and the molecules are essentially moving in any direction they want to move and at various different speeds. Hardly any of them are connected together anymore. So when you increase the temperature from a gas state into a plasma state, let's say into the thousands of Kelvin, what you're doing to these molecules is you're disassociating them into atoms. So I'm going to draw the molecules as the black, but the atoms as the red. And so we have the molecules moving about, and we have more atoms than molecules. Now, as you increase the temperature of the plasma up into the millions, what you're going to end up with is these atoms that have lost their electrons. So they're going to be ionized. So I'm drawing these ions as little plus symbols to indicate showing that the atoms have been ionized, and they lost their electrons, so the electrons are drawn as green, and they're traveling off in different directions. So as you increase the temperature, you go from the solid state where all of the molecules and atoms are bound together, such as in water ice. You increase the temperature and you start breaking these bonds. And so you start to have some free particles and some still bond in the liquid state. And then as you increase the temperature and you get this steam or this gaseous state, then what you have is you have all the particles that are no longer connected together. No more bonds. They're all free to move about in all different directions. And so when you enter into this plasma state, you start breaking these molecules up into atoms. And as you increase the temperature even further, these atoms start to lose their electrons. And so as you increase into the millions and millions of Kelvin, more of these electrons are free, and you have much, much more ions than you do of atoms. And these are the phases of a solid going to a liquid, to a gas, to a plasma state, or degrees of plasma state in increasing temperatures.